Hello, everyone. Welcome back to the ICP Bitcoin DeFi Bootcamp. Today we have our introduction to Solana integration. So I hope you're all up to date on our two previous introductory workshops because today is the third of the core content before we move on to some demo workshops later on in the series. So I'm going to invite our speaker, Louis, up to the stage from Dfinity Foundation. We're really excited to have him here today. Hi, Louis. Thanks for joining us.
Hi, everyone.
So we are going to jump right in. As always, everyone, if you have any questions, please put them in the chat. I did love the spirited debates we had in the chat last session, but let's try and keep focused on the technical content in the lecture so that you don't have to catch up later. And if you do have any questions relating to the lecture, make sure you put them in the chat and we will get to them towards the end of the session. But otherwise, I'm going to hand over to you, Louis, and we can get started.
Great. So I'll start by sharing my screen. And I believe you should all be able to see my slides now, right?
Yes, looking good.
Great. Yeah, so my name is Louis. I'm a software engineer here at the Dfinity Foundation. And today I'll be talking about the Solana integration with ICP. So throughout the slides, you'll see that there are some QR codes sprinkled here and there. So feel free to scan them, open them now or later, including a QR code here that links to the slides, and the other QR codes throughout generally link to some external references if you feel like reading up on a bit more in detail. So let's get started. I'm going to start with a short refresher on the ICP as a whole and how it works. So the ICP is a decentralized and permissionless cloud built on blockchain technology. A little bit of a bottoms-up approach. So let's start with the data centers that are operated by node providers. The node providers run nodes, potentially more than one node per data center. And the nodes come together to form subnets, where every node can only be part of one subnet. And a subnet is really an independent blockchain. So it's a replicated state machine, meaning that each node within the subnet performs the same computation on the same input and performs or achieves consensus on the result, on the output, and on the updated state. As we can see, the IC essentially consists of many individual subnets that are running in parallel. So something very special about these subnets is that they can seamlessly communicate with each other, even though they're essentially separate blockchains. And in turn, what this means is that smart contracts on one subnet can communicate with smart contracts on any other subnet. And this really allows the IC to scale horizontally. So if we need more computation power or more storage capacity, we can just add more nodes and form a new subnet. Now, canisters are at the core of the IC, and you can really think of them as an evolution of more classical smart contracts. It might be easier to think of them as decentralized servers. And they really have a lot of exciting capabilities. But today we'll focus on two that are really crucial for us with the integration with Solana, and namely HTTP outcalls. So the ability for canisters to call into Web 2 services and essentially interact with the outside world, as well as chain key signatures. So canisters have control over unique ECDSA or Schnorr key pairs and can securely request signatures. And this enables us, right, to interact, namely with Bitcoin, Ethereum, and today we'll focus on Solana. So Chain Fusion, it's a little bit of a broad umbrella term used to describe many things that the IC does. And it basically refers to the ICP's ability to interact with other blockchains. And the idea, right, is to bring everything together and use the features of other blockchains together with the unique features of the ICP into a single dApp. And supported chains until now, last week there was a talk about the integration with Bitcoin. There's also an integration with Ethereum, as well as most EVM and EVM-based L2s. And today, of course, we'll focus on Solana, for which we'll be focusing on threshold Schnorr signatures, as well as the Sol-RPC canister, which was rolled out just a few months ago. And so we'll really be looking at two key building blocks. First of all, of course, in general, to integrate with another blockchain, you need to be able to read and write. And there are two ways of doing this, either the Bitcoin API for Bitcoin, which is more of a bit of a at the protocol level integration, but there are also HTTP outcalls and RPC canisters, and that's what we'll focus on today because that's how the integration with Solana is done. But we also need to sign transactions to be able to interact with other blockchains, and for this we'll focus on the threshold Schnorr API today. Which, by the way, Solana uses threshold EDDSA, and EDDSA is covered by threshold Schnorr. We'll cover this more in detail later on. If you're interested in reading about other chains, feel free to scan the QR codes at the top right. So the integration with Solana, what is it actually? In one sentence, the Solana integration allows canisters on the internet computer to receive, hold, and send Sol, as well as other Solana tokens, all directly with transactions on the Solana blockchain. So since we're talking about Solana, let's start with a short overview of what Solana is and how it works. And we'll get started right away with some quick facts about Solana. And in the next couple of slides, we'll dig deeper into some of these concepts. So Solana was launched in 2020. Its consensus is based on proof of stake as well as proof of history. It has a very fast block time of about 400 milliseconds. And we can contrast this with Bitcoin's one block every 10 minutes, or the ICP's one block roughly every second. Its fees are very low and predictable. It's based on an account model, which again contrasts with Bitcoin's UTXO model. It enables smart contracts. For signatures, it uses EDDSA, as I just mentioned, which is covered by Schnorr, as a Schnorr type of signature. And so I'll generally not mention EDDSA again today, but I'll talk about Schnorr since that's the name of the feature on the ICP. Solana is used most in the ecosystems of meme coins, NFTs, and DeFi. Its native currency is Sol, which is currently valued at about $243. It has a TVL, or total value locked, of $13 billion and a market cap of around $132 billion. These numbers, I think, are from earlier today. You can scan the QR code at the top right to find the latest numbers. But generally, Solana is it's the third largest blockchain behind Bitcoin and Ethereum. So I mentioned proof of stake and how this is different from Bitcoin's proof of work. So what is proof of stake? First of all, proof of stake is actually what many other blockchains use. So Ethereum and ICP are two of them, but it works as follows. Validators lock up tokens, which is so-called staking, to earn the right to validate blocks. And the selection on who gets to validate the next block is random, but weighed by the amount of tokens locked. So for proof of work, like with Bitcoin, you're rewarded if you invest more in more mining hardware and more energy, whereas for proof of stake, you're rewarded rather if you stake more tokens. And generally, this, as you can imagine, since you don't need all this computation to calculate the next block as opposed to proof of work, it's much more energy efficient and enables higher transaction speeds and scalability. I mentioned proof of stake is used by Ethereum and ICP, but proof of history is something that's a little bit more unique to Solana. and it's meant to act as a cryptographic clock to prove that time has passed. For us, the most relevant thing, and we'll come back to this later, because it's relevant to the integration with ICP, the most relevant thing is that to be able to submit a valid transaction, you need to include the hash of a recent block, so in the last minute or so, for your transaction to be valid and actually mined. That's the consensus methods of proof of stake and proof of history. And let's now move on to the account model. Again, this is very different from Bitcoin, but if you're more familiar with Ethereum or even to some extent the ICP, this will be more familiar to you. Essentially, everything in Solana is an account. By account, we mean it's a stateful data container. And the simplest type of accounts are system accounts that essentially just hold a balance in Sol. If you recall, Sol is the native currency of Solana. And so, for example, we can consider just a very basic example here where we have two accounts. We have Alice's account and Bob's account. Alice has 5 Sol and Bob 15. And what happens is you have a transaction that comes along in a block, and the transaction includes an instruction to transfer some funds from Bob to Alice. So Solana transactions include instructions on the accounts. And so, for example, this instruction here transfers 5 Sol from Bob to Alice. And we can see that once this transaction is executed, the state in the accounts is updated accordingly. Program accounts are another type of account on Solana, and they are essentially smart contracts. They hold executable codes, not just data. So an example would be an application that allows you to borrow some Sol against an NFT that you own. And transactions, as I mentioned, contain instructions, and there's the basic type of transfer instructions that just transfer some funds around, but you can also send instructions to program accounts. And so, for example, if we have a very basic counter example here, so it's an account that contains executable code that is a counter application, we can have a transaction that calls the increment method on that counter. And once this transaction is executed, it will update the state accordingly. Of course, that's a very basic example, but that's the core of how smart contracts work on Solana. One actually concrete example of a program account is a very special program account. It's the Solana Token Program, or SPL for short. And you might be familiar with this. It essentially is how tokens are handled on Solana. And so it has special instructions that allow creating and managing tokens, minting tokens, and the like. And how tokens are handled on Solana is essentially that there is a mint address that is allowed to mint and burn tokens, so create and destroy tokens. And so you can see that, for example, USDC, USDT, or Trump coin are all examples of tokens on Solana. So you have stable coins, meme coins, and the such. And system accounts, I mentioned, are the accounts that hold balance. They can't quite hold a balance in tokens, but there is a concept of an associated token account, which is an account that's linked to a system account, and that's meant to hold the balance for a specific token. So, for example, Alice might create a USDC token account or a Trump coin token account, and then be able to manage her balance there. And so now that we covered a few basics about Solana, let's move on to how the ICP actually interacts with Solana. And for this, the first building block we need is the JSON-RPC API. So what is it? The JSON-RPC API is basically the official interface for talking to the Solana network. And it's a JSON-RPC interface over HTTP or WebSocket that lets you either query the state of the blockchain, like balances, account information, programs, and such, or modify the blockchain state by submitting a transaction, or even subscribing to events over WebSockets. This last point is something that's not currently available on the ICP, but the first two are available, as we'll see later. And so some examples of endpoints that are exposed by the JSON-RPC API are get balance to get the balance of an account, or getting the account info, sending a transaction. This interface is basically how wallets, explorers, dApps, and SDKs communicate with Solana. So what's this big acronym? JSON-RPC API. I'm sure most of you are familiar with at least the first one. JSON, JavaScript object notation, is just a way of formatting data. RPC stands for remote procedure call, which is a fancy name for basically calling methods on a server. And API, I think, needs no introduction. Essentially, all of this means that the JSON-RPC API defines an interface, or it defines a format for how you can structure requests to the Solana network. So such an example request is here on the bottom left. And also, this interface specifies the format of the return value. So here you have an example where you would want to get the balance of a specific account. And this big string in the middle, this big random-looking characters in the request, this would be the address of an account. And so this corresponds to a request to get the balance of a particular account. And then on the right, you would have the return value with some extra context information, as well as the actual balance value next to the value keyword. So RPC providers are just as important. RPC providers essentially run, these are entities, usually companies, that run blockchain nodes or clusters of nodes and expose this JSON-RPC API to clients. And the reason for this to exist is that instead of running your own full Solana validator node, which is complicated, you can essentially use the services of an RPC provider to make your requests, your JSON-RPC request to them, and you trust them that their response is accurate. So they do the direct interaction by running their own node. And so, whereas with the Bitcoin integration, there is essentially a direct integration with the blockchain. With Solana, you can see that we're actually going through intermediaries, which are RPC providers. But as you'll see, we offer some infrastructure to essentially aggregate the response from multiple providers and make sure that we don't rely on a single one. So now that we looked at the interface to interact with Solana, the JSON-RPC interface, let's see how to actually use this interface from a canister. And this is, of course, done via HTTP outcalls. So what are HTTP outcalls? Simply put, HTTP outcalls allow smart contracts to directly make HTTP requests to external Web 2.0 servers. And this way, we don't have to rely on oracles to obtain external data, and we can actually interact with the off-chain world, such as we'll see later, RPC providers. To summarize very quickly, for HTTP outcalls, each replica, so each node in a subnet essentially, pushes their potentially transformed instance of the received HTTP response from the web server that they made the request to through the internet computer's consensus layer. And the optionally transformed here is important. You can imagine that raw HTTP requests actually contain a lot of noise, for example, timestamps. And this would, so achieving consensus on the raw response would not be possible because each each node in the subnet, each replica in the subnet would essentially have a different value of a timestamp or other headers, and they wouldn't be able to achieve consensus on this. So this transformation is crucial. It gets rid of what we don't need and only keeps what we need and what we can actually achieve consensus on. And so using HTTP outcalls, canisters can read Solana state. They can make an HTTP outcall via the HTTP request management canister method. So they make a request to one of the RPC providers. The RPC providers then interact directly with the Solana blockchain and return the response. But canisters can also write to Solana state using HTTP outcalls. And this is just done with different JSON-RPC methods. So there is the send transaction method that allows to post a transaction to the Solana blockchain. The difference being that to be able to send a transaction, it needs to be, and for it to be valid, it needs to be signed. And this leads us to the next building block that we need for the Solana integration, which are threshold signatures. And so chain key signatures, I'll use the terms pretty much interchangeably since they essentially refer to the same thing. But chain key signatures consist of a threshold signature scheme where the private key is held in a secret shared manner by the replicas. So what does this mean? Generally, threshold signatures is not something that's unique to DFINITY or to the ICP. Threshold signatures are a cryptographic method that allows splitting a key into shares, so a private key into shares, and obtaining a signature for the original key by combining the signatures that were made by the individual shares. And you can split the original key in a way that you don't actually need all of the shares to build your signature. So for example, you might only use a 2 out of 3 thresholds, and that's where the name threshold comes in the threshold signature name, to be able to recover a signature for the original key. And also very importantly, once you split your key like this, you cannot recover the original key from any one of the key shares. So nobody here, if you distribute the key shares across different servers, none of the servers are actually aware of the original secret key. So how does this work with the IC? Chain key signatures on the IC come in 2 flavors, threshold ECDSA and threshold Schnorr signatures. For Solana, we're integrated in threshold Schnorr, which includes EDDSA, as mentioned earlier. And those are the types of signatures that are relevant for Solana, since that's what is used in transaction signatures. And there are threshold signing subnets for Schnorr and ECDSA. In those subnets, essentially, there is a master key that's split up into secret shares, as I mentioned, and each share is stored on a different node of the subnet. At the moment on the subnets, there are 31 nodes, so the secret keys are split into 31 shares. To sign a message, the nodes on the signing subnet need to coordinate to generate the signature in a distributed fashion, and at least 1/3 of the nodes is required to jointly create the signature using their key shares. Canisters can therefore request a signature using a request to that subnet. So they send their message, and they can the canisters on the signing subnet, or actually not the canisters but the replicas, will do the actual signing. So here, a little bit more in detail. What's also very important is that canisters can actually control their own key pairs based on their principal ID. So the principal ID is essentially the unique identifier of a canister, but also of other users on the ICP. And this is done through chain key derivation. Again, key derivation is a general concept, especially used in elliptic curve cryptography. But the idea is that it's a cryptographic process that deterministically generates unique keys from a root key. So you have a master key or a root key, and together with a derivation path, so another number essentially, or a hex string or something like that, you can obtain a new key pair. And so this way, canisters have control over a unique Schnorr key derived using their principal ID. And they can request signatures with the corresponding private key to be computed on the threshold signing subnet. even though nobody actually has the private key ever reconstructed. So the canister doesn't have access to its own private key, but it requests a threshold signature from the threshold signing subnet, and it's then reconstructed from all the shares, and they can have then a signature for their own private key derived from the root or the master key and their own principal ID. And so also we can go one step further and derive, for example, let's say we have a wallet application, it can derive further private keys that are derived using a user's principal ID. So you can take the canister ID, the canister key, which is derived from the master key, and derive then individual keys for the users, which then require the principal ID of the user to be to get a signature. So I won't go too much more into detail. This is probably the most technical part of the talk. But just to give you an idea, you have two methods that are available to canisters and that basically make up the chain key schnorr feature. And there's one method on the left to actually get a public key given a canister ID and derivation path. And then there is a method to sign with a key. And you can see that you don't pass the canister ID to the signature method because you're not able to spoof another canister ID. So you can only sign with keys derived with, so a canister can only sign with keys derived from its own ID. So the takeaway here is that canisters have their own Schnorr keys and they can sign using these keys. They can get a signature. And so once they build a transaction, they can then make a request to the threshold Schnorr subnet to get this transaction signed. And so they can also make a request to get the public key, and they can make a request to sign a transaction. And since transactions on Solana are signed with EDDSA or Schnorr, this means that canisters can sign Solana transactions. So now we have all the building blocks we need for actually interacting with Solana from the internet computer, and we'll now cover some of the features or some of the capabilities of the Sol-RPC canister. And this is an infrastructure canister maintained by the DFINITY Foundation that essentially offers an easy-to-use interface for canisters to interact with Solana. So we've seen that HTTP outcalls and threshold signatures give us all the building blocks we need to interact with Solana, but still, building a canister that securely and correctly interacts with Solana can be challenging. There's a lot of ways to shoot yourself in the foot. So we provide the Sol-RPC canister, which essentially acts as a gateway to Solana. It's essentially a helper canister that does a lot of the heavy lifting for us. It allows canisters to interact with Solana via inter-canister calls. It essentially hides away the whole HTTP outcall aspect. And so here we have a little diagram of how this would look like. On the far left, we have a normal canister. In the middle, we have the Sol-RPC canister. And so if our dApp on the left wants to, for example, make a get balance request, it would make an inter-canister call to the corresponding endpoint on the Sol-RPC canister. The Sol-RPC canister will then make the required call to an RPC provider, which will then, or to multiple RPC providers, it will then aggregate the response and send it back to the original dApp. And this really allows developers to focus on their actual use case instead of reinventing the wheel and replicating the necessary logic to interact with Solana. So the Sol-RPC canister does many things. Mostly, it creates the HTTP requests and parses the responses from RPC providers. Very importantly, it aggregates their responses, reducing the risk of centralization and bottlenecks. It also takes care of managing API keys. As I mentioned, RPC providers are usually external companies that this is a paid service, and managing API keys can be a pain. So all of this is done by the SolRPC canister, and the cost of these subscriptions is included in the request fees. It also takes care of cycle management for HTTP outcalls. Importantly, it also takes care of consensus issues due to Solana's fast block time, and allows interacting with Solana via inter-canister calls instead of HTTP outcalls. Going one step a bit more in detail, it includes endpoints for reading state from Solana, for example, getting the current slot or the balance of an account. You can also write state by sending a transaction. You can also interact with SPL tokens that we mentioned earlier, for example, getting a token account balance. And any endpoint that we don't explicitly support can always be interacted with via the request endpoint, which allows specifying essentially the raw JSON-RPC request. And now I want to talk a little bit more in detail about some of the consensus errors that are actually caused by Solana's fast block time, and that the SolRPC canister helps managing. Just to put things back in context, I mentioned at the beginning that Solana's block time is about twice as fast as the ICP. And also if you take into account some cross subnet request times and things like this, the value of some things on Solana can change much quicker than a request might be executed. So I also mentioned that something that's needed for building Solana transactions is for the so-called POH, or proof of history, is a recent block hash. And the canonical way of doing this is by calling the get latest block hash endpoint from the Solana JSON-RPC API. The problem is that this value just changes too quickly. And so if a canister would just try to make an HTTP outcall to the get latest block hash method of the Solana JSON-RPC API, it would get each replica would essentially make their request at a slightly different time and get a different hash value, and then there is no way to achieve consensus on this. A solution for this is essentially to break things up into two. And so we start by looking at the get slot method. So what the SolRPC canister does is, instead of using the get latest block hash method directly, it calls the get slot method instead, which returns the index of the latest block on Solana. And here the difference is the replicas will still see a different value, maybe 501, 502, 506, that differ slightly, but we can apply a transformation to the result that we get to our response. For example, we can round it down to the nearest 20 and all agree on the value 500. And so we have a value that's close enough, it's recent enough that this block can be used for proof of history. And so once we have the value of get slot, we can make a second request to the get block method for that particular slot, that particular index, and then just extract the hash value of that block. And so this is one example of the difficulty of working with Solana from the ICP, just because Solana's block time is so fast. And so let's look on a very high level how it looks like if we, for example, have a dApp on the far left here that wants to build and send a transaction on Solana. So it would start with step one by doing what we just outlined, essentially fetching a recent block hash with get slot and get block. This information would be fetched by the SolRPC canister from the Solana blockchain via RPC providers. It would then return this information to our dApp, which can then create a Solana transaction. It can then make a cross-subnet request to sign that transaction with threshold schnorr. And finally, it can make another request to the SolRPC canister to actually send that transaction. And the SolRPC canister, as a last step, can submit this transaction to the Solana blockchain. So let's look again at this example, how to actually build and send the transaction, but just a little bit more in detail and what's going on behind the scenes. So you can see that this is a sequence diagram of exactly the information from the last slide. We start with a get slot request from our canister, our DApp canister to the SolRPC canister. The SolRPC canister then makes this request via HTTP to various RPC providers, aggregates the response, sends it back to the DApp. Same thing happens for the get block request. Once our DApp has all the necessary information, it builds the unsigned transaction, signs the transaction with Schnorr by making a request to a signing subnet. It then makes a send transaction request to the SolRPC canister, which then again interacts with the RPC providers to send the transaction and finally sends back the transaction hash. And so there are a couple of things going on here, right? In this red square, or rectangle, I've highlighted all of these are inter-canister calls. So you can see that the DApp that's at the center of this, our kind of starting canister, doesn't actually make any HTTP outcalls directly. It's only interacting with the SolRPC's inter-canister interface or candid interface. We also have HTTP outcalls, and this takes place between the SolRPC canister and the RPC providers. First, looking at it a different way, first we perform some read operations to read the current slot and block. And finally, we write state to the blockchain. So as a short aside, some of you might be aware that there is actually a bit of a caveat to proof of history. There is an alternative on Solana for building transactions to fetching a recent block hash, because this is kind of annoying, right? On the ICP. And there is an alternative, and this is called durable nonce. And a durable nonce, basically what you do is you create a special nonce account. And when you submit a transaction, you can essentially include the nonce value from that special account instead of a recent block hash. The caveat being that when you submit your transaction, you also need to prove that you are using this nonce value only once. So in the same, when you submit your transaction, you also need to include an instruction to bump this value. So this can be nice and very useful if, for example, you need to pre-sign a transaction, right? If you want to already sign a transaction that might be executed later on, tomorrow, there is no other way of doing this. But this does have some drawbacks, namely single-use bottleneck. So nonce value can only be used in one transaction. And so you can only make one transaction at a time using a single nonce account. This means you also need to manage, take care of the account management. You need to create the account, which is a bit of a chicken and the egg. Creating the account requires to submit a transaction, and if you don't have a durable nonce account yet, then you need anyways a recent block hash. It's also more expensive usually because of managing the account, and so on and so on. So it definitely does have some use cases, and by the way, this is also completely doable with SolRPC canister. We have some examples available, but has to be considered carefully. So I'd now like to refer you to some resources that we have, and namely the basic Solana wallet example. And so if you really want to dive into the code and get a feel for this, play around with a canister that interacts with Solana, this is it. It's available on GitHub. It includes examples of managing balances, submitting transactions, examples of durable nonces, and also examples of interacting with SPL tokens. So for example, if you want to send around some USDC on Solana, this is totally doable. It's available on GitHub. There's a QR code at the top here. It's on the SolRPC canister repository available under the Dfinity Foundation's account. Also worth mentioning is ICP Ninja. I don't know if all of you know about ICP Ninja, but it's essentially it's a very cool online in-browser IDE that takes away a lot of the hassle from deploying and managing canisters. It's completely free at the beginning, at least, and you can create an account so that your canisters are longer lived. And there is this basic Solana wallet example I just mentioned is already available on ICP Ninja on the front page. But you can also go, if you happen to be in the GitHub repository of the SolRPC canister, there is a link that will lead you to ICP Ninja and open the accounts directly. So if you don't have all the setup on your machine, you can really just go to ICP Ninja, click on the basic Solana example, and you'll be linked straight to the code. You can click run and it'll deploy the canister that you can interact with right away. Finally, to kind of close off this presentation, no worries, there's time for questions. We will also, you can also check out bitcoindefi.dev with some examples of successful projects built using Chain Fusion on the ICP and most notably Bitcoin, but also Solana. And this is the best way to continue learning and start experimenting. Here are a bunch of resources. Feel free to scan all the links there and check out the basic Solana example, the integration demo videos, and all the ICP documentation. So this wraps it up for the presentation, but I believe until 6 we have time for questions. So I will go back to here, and feel free to shoot. I didn't check out the questions in the chat, but
so we've had some questions throughout. For anyone whose question, if it's not got enough context, maybe put it back in chat again with a bit more context. I think Lorraine was asking why are event subscriptions to do with WebSockets, why are they not available on ICP? It was something you mentioned earlier.
That's a good question. It is definitely a nice feature of Solana. The problem is currently there's no support for WebSockets on the ICP. So there's only normal HTTP outcalls, no WebSocket equivalent. And so event subscriptions rely on WebSockets.
Jilt asked, does the RPC return data to detail the type of account that you're interacting with on Solana?
So I'm not sure exactly here. Yeah, I see that they're typing, right? But so there's actually different methods. So there's one for interacting with, or I guess it doesn't generally give too much information. There are different ways of returning the encoded account information. So you can return it either as it's already like a formatted JSON or just a raw base64 encoded, potentially compressed information, and then you have to extract it. But generally this returns like the structure of the account and generally what type of account it is.
I think for some additional context, Joseph was asking to do with security. I'm not sure.
So I'm not sure. I'm not sure here.
If you want to, if your question hasn't been answered as like what it is that you're kind of looking for, just give a bit more context, and we'll be able to help you out. Israel asked, do HTTP outcalls also occur in burner addresses on Solana?
I don't know what this would mean with occur. So generally HTTP outcall is something that a canister would do on purpose, right? This is something that's purely, let's say, an ICP feature. But if I'm not sure about the word occurs here, but you can perform an HTTP outcall to get information about a burner address, for example.
Emmanuel was asking about chain key signatures and threshold signing. They thought it was unique to ICP, but I think you mentioned it's not. Can you explain a bit more about that?
Yes. So maybe the wording there was a little bit not clear. So generally, chain key signing is something that's unique to the Dfinity blockchain, but the mathematics behind threshold signing, this is definitely not only at Dfinity, although there were definitely some very important, very cool papers, for example, developing a threshold signing for ECDSA this was a lot of done work at Dfinity. But if you look up threshold signatures and ways to sign basically using parts of a share of a key, there's a lot of resources out there that are not just from Dfinity. The thing that's unique to Dfinity is that you can do this on the blockchain and within a smart contract.
And then Emmanuel also asked a little bit later, since there's already a Sol-RPC canister on ICP, why do you still need to talk to the RPC endpoints and not just communicate directly with the network?
Yeah, that's a very good question. And so I quickly glanced over the fact, right, that with Bitcoin integration, we are talking to the Bitcoin network directly. This is a bit of a question of resources. Generally, running a node is expensive and difficult. And so it's just easier to interact with, and just more applicable, more let's say more well-suited to the ICP to interact via the RPC interface.
Jill has followed up. They'll check GitHub, but what was described was the fact that only ICP to Solana transfers can be safe. The Solana part needs to be done on the Solana side with a deployed smart contract. Is that right?
So I believe so. I believe now I don't remember exactly the details. There are some things that are tricky with monitoring accounts, and this is linked to the first question actually I think we got with subscribing to events, because it is difficult to monitor accounts on Solana because we don't support WebSockets. I believe this does make things a little bit trickier here. But yeah, I think, for example, ConkSwap already offers transfers both ways, so this is definitely doable.
I think Israel might be in the middle of typing another question. So we might have a couple more. Oh, do you want to coin swap? What's the...
ConkSwap is KONG, like King Kong, or it's a DEX on it's running on the ICP.
Nice. So you might be able to find that on the ecosystem page, Jill, to have a look at that.
DEX is a decentralized exchange, by the way.
Israel has asked, for network overload usually happening in Solana, does it affect the Solana running on ICP?
So I'm not sure exactly here with network overload. Generally, I mean, if there are issues on the Solana blockchain, how this might have repercussions on the Sol-RPC canister is simply that we won't be able to fetch this state for some time, right? So if there's a problem, generally, when was it that the Solana network was essentially down for a little bit of time, right? Obviously, during that time, you won't be able to fetch or write state to the Solana blockchain.
That makes sense.
Yeah.
Israel, if you have another follow-up, put that in chat. So from a security perspective or keeping assets safe, if there was an issue on Solana, would that then...
I guess I'm not sure here, would you be safekeeping some Solana assets from a smart contract or from a canister on the ICP? Is that the question? So generally, I guess the main thing, right, with this integration is that you can essentially do anything that you would be able to do on the Solana network, but from a canister. So if something is safe to do on Solana, it's more or less, if implemented correctly, then safe to do from within the canister, so you can manage your assets there. If there's a time, for example, where transactions are not going through on the Solana network due to the whole network being down, then your assets are not going anywhere, right? But this doesn't necessarily make it safer or less safe by keeping them on the, or by managing them from the ICP. So network issues, I guess this would be a problem with RPC providers generally. So RPC providers are not 100% foolproof, right? They sometimes have issues. I mean, there's the type of issue where the whole Solana network might be down. This doesn't happen very often, but it has happened. In this case, there's nothing much we can do. But one reason for using multiple RPC providers is that if one of them has a problem, then we can still rely on the remaining ones to read and write states.
Hopefully, Israel, that's kind of answered your questions. If you do have any follow-ups, though, you can put them in Discord, and we might be able to get you some useful links as well if you wanted to read a bit more. Thank you very much, everyone, for coming along to our third session in the bootcamp. I hope you found today's session, last week's sessions really useful in setting your baseline for the bootcamp. As next up, we're going to dive into some demos of projects being built on Bitcoin on ICP. So I hope you're really looking forward to that. As always, the recording for this session will be available. So if you want to go back over and review anything that Louis has taught, you can do that after the session, and we'll put some of the useful links that are in the slides as well available for you to click through and read a bit more about. Thank you very much, Louis, for coming in and teaching. It's been a real pleasure to have you, and thank you for answering everyone's questions. I hope we see you around in some more Code Club bootcamps. Everyone, unless you have any other questions, we'll end the session for today, and we'll see you all again on Wednesday for our second workshop of the week.
Thank you all for having me. It was a pleasure.
See you soon, everyone.